Sometimes the best designed experiments fail. The effect you're looking for might not even be present, meaning that a null result should always be a possible outcome you're prepared for. When that happens, the experiment is often dismissed as a failure, even though you never would have known the results without performing it. While obtaining constraints on a phenomenon's existence or non-existence is always valuable, sometimes even revolutionary, as in the case of the famed Michelson-Morley experiment, it's usually disappointing when your search comes up empty. Yet, every once in a while, the apparatus that you build might be sensitive to something other than what you built it to find. When you do science in a new way, at a new sensitivity, or under new, unique conditions, that's often where the most surprising, serendipitous discoveries are made. When you're capable of probing nature beyond the known frontier. In 1987, a failed experiment for detecting proton decay succeeded in detecting neutrinos, for the first time, from beyond not only our solar system, but from outside of the Milky Way. This is the story of how the science of neutrino astronomy was born. The neutrino is one of the great success stories in all the history of theoretical physics. Back in the early 20th century, 3 types of radioactive decay were known. Alpha decay, where a larger atom emits a helium nucleus, jumping 2 elements down the periodic table. Beta decay, where an atomic nucleus emits a high-energy electron, moving 1 element up the periodic table. Gamma decay, where an atomic nucleus emits an energetic photon, remaining in the same location on the periodic table, but transitioning to a more stable state. In any reaction, under the laws of physics, whatever the total energy and momentum of the initial reactants are, the energy and momentum of the final products need to match. That's the law of conservation of energy. For alpha and gamma decays, energy was always conserved, as the energy and momenta of both products and reactants matched exactly. But for beta decays, they never did. Energy was always lost, and so was momentum. The big question, of course, was why. Some, including Bohr, proposed that the conservation of energy was not sacred, but was rather an inequality. Energy could be conserved or lost, but not gained. However, in 1930, an alternative idea was put forth by Wolfgang Pauli. Pauli hypothesized the existence of a new particle that could solve the problem, the neutrino. It wouldn't absorb or emit light and would only interact with atomic nuclei extremely rarely and extremely weakly. Upon its proposal, rather than feeling confident and elated, Pauli felt ashamed. "I have done a terrible thing. I have postulated a particle that cannot be detected," he declared. But despite his reservations, the theory would eventually, a generation later, be vindicated by experiment. In 1956, neutrinos, or more specifically, antineutrinos, were first directly detected as part of the products of a nuclear reactor. When neutrinos interact with an atomic nucleus, 2 things can result. They either scatter and cause a recoil, like a billiard ball knocking into other billiard balls, or they get absorbed, leading to the emission of new particles, which will each have their own energies and momenta. Either way, you can build specialized particle detectors around the area where you expect the neutrinos to interact and look for those critical signals. This was how the first neutrinos were detected, by building particle detectors sensitive to neutrino signatures at the edges of nuclear reactors. Whenever you reconstruct the total energy of the products, including the hypothesized neutrinos, you find that energy is conserved after all. In theory, neutrinos should be produced wherever nuclear reactions take place, in the sun, in stars and supernovae, and whenever an incoming high-energy cosmic ray strikes a particle from Earth's atmosphere. By the 1960s, physicists were building neutrino detectors to look for both solar, from the sun, and atmospheric, from cosmic ray neutrinos. A large amount of material, with mass designed to interact with the neutrinos inside of it, would be surrounded by this neutrino detection technology. In order to shield the neutrino detectors from other particles, they were placed far underground, in mines. Only neutrinos should make it into the mines. The other particles should be absorbed by the Earth. By the end of the 1960s, solar and atmospheric neutrinos had both successfully been found via these methods. The particle detection technology that was developed for both neutrino experiments and high-energy accelerators was found to be applicable to another phenomenon, the search for proton decay. While the standard model of particle physics predicts that the proton is absolutely stable, in many extensions, such as grand unification theories, the proton can decay into lighter particles. In theory, whenever a proton does decay, it will emit lower mass particles at very high speeds. If you can detect the energies and momenta of those fast-moving particles, you can reconstruct what the total energy is and see if it came from a proton. If protons were to decay, we already know that their lifetimes must be extremely long. The universe itself is 13.8 billion years old, but the proton's lifetime must be much longer. How much longer? The key is to look not at one proton, but at an enormous number. If a proton's lifetime is 1030 years, you can either take a single proton and wait that long, a bad idea, or take 1030 protons and wait 1 year, a much better, more practical, to see if any decay. A liter of water contains a little over 10 power 25 molecules in it, where each molecule contains 2 hydrogen atoms, a proton orbited by an electron. If the proton is unstable, a large enough tank of water, with a large set of detectors around it, should allow you to either measure the lifetime of the proton, which you can do if you have more than 0 decay events, or to place meaningful constraints on the lifetime of the proton if you observe that none of them decay. In Japan, in 1982, they began constructing a large underground detector in the Kamioka mines to perform exactly such an experiment. The detector was named Kamioka Neutrino Detector Experiment. It was large enough to hold over 3,000 tons of water, with around 1,000 detectors optimized to detect the radiation that fast-moving particles would emit. By 1987, the detector had been running for years, without a single instance of proton decay. With over 10 power 31 protons in that tank, this null result completely eliminated the most popular model among grand unified theories. The proton, as far as we could tell, doesn't decay. Kamioka-NDE's main objective was a failure. 165,000 years earlier, in a satellite galaxy of the Milky Way, a massive star reached the end of its life and exploded in a supernova. On February 23, 1987, that light reached Earth for the first time. All of a sudden, we found ourselves observing the closest supernova event we had seen in nearly 400 years, since 1604. But a few hours before that light arrived, something remarkable and unprecedented happened at Kamioka NDE. A total of 12 neutrinos arrived within a span of about 13 seconds. 2 bursts, the first containing 9 neutrinos and the second containing 3, demonstrated that the nuclear processes that create neutrinos do, in fact, occur in great abundance in supernova. We now believe that perhaps as much as 99% of a supernova's energy is carried away in the form of neutrinos. For the first time ever, we had detected neutrinos from beyond our solar system. The science of neutrino astronomy suddenly advanced beyond neutrinos created either from the sun or from particles colliding with Earth's atmosphere. We were truly detecting cosmic neutrinos. Over the next few days, the light from that supernova, now known as SN1987A, was observed in a huge variety of wavelengths by a number of ground-based and space-based observatories. Based on the tiny difference in the time of flight of the neutrinos and the arrival time of the light, we learned that neutrinos traveled that 165,000 light-years at a speed indistinguishable from the speed of light, that their mass could be no more than the mass of an electron, and that neutrinos aren't slowed down as they travel from the core of the collapsing star to its photosphere, but electromagnetic radiation is. Even today, some 35 years later, we can examine this supernova remnant and see how it's evolved. The scientific importance of this result cannot be overstated. It marked the birth of the science of neutrino astronomy, just as the first direct detection of gravitational waves from merging black holes marked the birth of gravitational wave astronomy. An experiment that was designed to detect proton decay, an effort that still has yet to yield even a single positive event, suddenly found new life by detecting the energy, flux, and location on the sky of neutrinos emerging from an astronomical event. It also was the birth of multi-messenger astronomy, marking the first time that the same object had been observed in both electromagnetic radiation and via another method. It also was a demonstration of what could be accomplished, astronomically, by building large underground tanks to detect cosmic events, leading to a slew of modern, superior detectors such as Super-Kamiokande and IceCube. And it causes us to hope that, someday, we might make the ultimate trifecta observation, an event where light, neutrinos, and gravitational waves all come together to teach us all about the workings of the objects in our universe. In addition to being very cleverly repurposed, it resulted in a very subtle but equally clever renaming of Kamioka NDE. The Kamioka Neutrino Decay Experiment was a total failure, so Kamioka NDE was out. But the spectacular observation of neutrinos from SN1987A gave rise to a new observatory, the Kamioka Neutrino Detector Experiment. Over the past 35 years, this has now been upgraded many times, and multiple similar facilities have popped up all over the world. If a supernova were to go off today, anywhere from within our own galaxy, we would be treated to upwards of 10,000 neutrinos arriving in our modern underground neutrino detector. All of them, combined, have further constrained the lifetime of the proton to now be greater than around 10⁻35 years, a bit of tangential science that comes along for free whenever we build neutrino detectors. Whenever a high-energy cataclysm occurs, we can be confident that it creates neutrinos speeding all through the universe. We've even detected cosmic neutrinos from billions of light-years away. With our modern suite of detectors online, neutrino astronomy is alive, well, and ready for whatever the cosmos sends our way. Thank you so much for coming this far with us. Remember to join us next time, in the next video. Until then, take care and good night.